Morning mga Bisaya. So our topic for today is about display displays and anchors. And then these hairpins, although they are related, this one, but we will discuss this in a separate video because I will also discuss the we have a like a group like member of the group that asked me like about anchoring the trusses and it is related to this one also, so we'll just discuss that also together as a separate video from the base plates and anchors. So there was a post, or there was a a follower question, like asking me like about anchor bolts, and then I posted on my page that says you don't use structural bolts for as an anchor bolt, and then there was a reaction from another engineer saying that it's not only F1554 material that are used as anchor bolts, also the ESTM A325, A490, and A307, which is they are all structural bolts, which these are different. But anyway, so for this plate and anchor design, this is actually a design guide from EIEC. You know? So from EIEC, they have, if I believe, about 36, 35 design guides. No? So design guides. So if you just if you are interested or if you are looking for a specific design guide, you just look at the list from EIEC, and then or let's try see if we can find one. Let's see if we can find the list. EIEC. So these are the list of EIEC design guides. So we have design guide one, like the one I'm discussing, or we will be discussing today is about the design guide one, base connection design for steel structure steel edition. And then design guide two is design of steel composite beams one with web openings. Then the three serviceability design, five, I don't know where's design guide four. And then six composite column, seven design building, design guide, partially restrained composite connection, design guide 8, 9, and so on and so forth. Like 35, 36, 37, 38, 39, 40, 41. So there are already 41 design guide. So, well, if you are a member, it is free. And then if you are not, then that's $60 each. So that's if you're not a member, that's what 60 times 41. So that's 2,000, 1,060, 1,460. That's a lot of money. So that's why it's better for you to just, get membership. It's nice to have, all these design guides. Although you may not need all of these, but I would say most of it you will need it. So going back, um, so this is design guide one, base plate anchor and uh, base plate and anchor design. Now I will emphasize again that for materials, so let's hear like material specifications. Now it is clearly, I mean, in the design guide, they have this recommendation. This plate should be designed using STM material, STM 836. So, and even the anchor bolts here says, see, ESTM E5, F1554 with grade 36 being the most common. So basically, if only like 836 can handle all the loads as much as possible, that's the grade that you have to use for like anchor bolts and um base plate. So um so right here, so base plate material and then grade 55 anchors are used when there are large tension forces due to moment connection or uplift. So if it's just like, for example, pre-engineered building, so what are the forces involved in a pre-engineered building? So if that is your building, the forces involved here are, of course, vertical, like gravity, and then, or I'm talking about reaction here, but we'll discuss. We'll write um the actual the building reaction or the building load, not the foundation reaction. So we have the vertical load, gravity, and then you have the uplift due to, of course, you have wind load, and then overturning, and then the shear. Because typically, pre-engineered building are pin connection. It is designed as a pin connection. So these are the only forces involved: shear, vertical gravity, and then vertical uplift for like wind suction on overturning. So those are the forces involved. So if the shear capacity of the anchor bolt is enough to handle the shear, like using 836, then it is preferred to use 836 unless you need really like, large, um if you have large tension load, and then you need bigger capacity, that if you use 836, say your rod diameter would require like, 2 inches or 3 inches. So it's no longer practical. So that's the time you use higher grade. But as much as possible, um, you use the 836. Now, for anchor bolt materials, so like I said in my previous post and video, that the E325, A325, A A307, that is considered also as an anchor bolt, because this is the same as grade 36. That's actually the same as grade 36. If you look at the tensile, the FU is 58, and then the same above value, like this one, 29, 29. See, this one, 836, this is different now with if, because this is considered, or not obsolete, but this is merged with E5, F1554, and simply called F1554 grade 36 instead of the usual, the old specs we say ESTM 836. So right now we say if ESTM if 1554 grade 36 instead of ESTM 836. So this is the new the latest material. So when you specify a anchor bolts, it will be this one here. Although you can still use the old, it's still the same. It's just at this time, like 836, the old 836 is being merged with F1554, and then 837, that is really that is also an old like material used in structural connection. Um, one commenter in my post said like they only use 8307 for erection and temporary like anchors, not the final. structural bolt. So I've read also from Portland bolt that says some engineers specify this one A325 grade, but in the specification you have to indicate it should be um, ESTM A325S. So there should be S. So that's how it's written in the in Portland bolt that I read. But 490 is definitely no. 490. One reason is these bolts are standard for structural connections, and E490, the maximum length I think, if I remember correctly, was 8 inches, and then this one is 5, I think, the standard length, because it basically designed for like steel connection, so you don't need really long bolts. So that's why it is not used, because if you use this kind of, I mean, this embedment here, then if you consider the projection, then I mean, for example, like if a steel building, your projection is a 2 inches or 3 inches projection, and then you are only have about 2 inches left for embedment, which is nothing. So, but this one, also like this material are tested for that specific application. So that's why it's better to just specify whatever is stated in the design guide. So we are using design guide after all. Like we are following like um EIEC or CIEC, so whatever it is. And then well, there's no one barred you from using other materials, but it's up to you. I mean, it's your call, it's your design. But if we have to follow the code, then these are the recommended materials. Now, with regards to welding plate, so there's a provision here. I mean, I would really suggest if you're into a steel design and metal building, warehouses, shops, whatever. If you are doing steel design, I would really recommend to at least get this guide. Not this particularly, because I think the one I showed you earlier, this there's already a third edition. Yeah, this one. So this is the third edition. So I don't know what changed from design second edition versus this one. So you better get the latest one. This the purple one. This one. Third edition. So so there's also a provision here. I only took like a screenshot of some of the provision in this design guide. So if I were you, I would really if you're interested with this design, I mean, if you're into steel, then you have to have this design guide, and then I mean it's about what 69 pages, all about base plates and Ancora design. It has examples and explanation why it's done that way, something like that one. So there's also a with regards to welding here. The circular column base plate welds may vary greatly between columns. Welds attaching base plate to columns are often sized to develop the strength of the anchorage in tension, which can be achieved with relatively small fillet weld. So basically, um, fillet weld is preferred versus groove weld, because fillet weld is cheaper. It is cheaper to do, and compared to groove welds. Um, and then there is this. I specifically screenshot this provision because of this one here. So the use of weld all around symbols should be avoided, especially on wide flanges shape. So, for example, if you have a you know um, if you have the HCC or the wide flange column, and then your base plate here, right? So avoid, it says that avoid an that symbol, that circle means all around in welding. So avoid this one here because the contribution, if looking at the cross section, this one here, the welding on this side like has little to no contribution to the actual capacity. Also this the fillet here. So as is here, flange and in the ranges between the wave add very little strength and are very costly. So um, especially if the load is only like for shear and uplift and compression. For bending, I will discuss another way of. I mean, for welding, yeah, you can weld the flange and the web, and then the inside portion of the flange here, but not all around. And then there's another way of resisting like high bending on your column base if you have say cantilevered column. So these are the different or recommended sizes for anchor bolt holes in base plate. Now these are standard sizes, and this is kind of a like a little bit bigger than the standard hole diameter for structural connection like beam to column connection or beam to beam. This one is a little bit larger because it accounts for like higher tolerance, and there's also a you can also do like a oversized holes, and then we will discuss that one later. Now I will also talk about this one here. Um, so the EIEC design guide itself referred to this provision from the from this safety and health regulations, the OHSA. So in the OHSA, this has something to do with steel erection. So all columns shall have a minimum of 4 anchor bolts or anchor rods for safety purposes. So regardless of um, what your structure is, um, unless it is like, you know, it is built on site or it is built on shop and then brought to site, like pre-assembled, really, that's fine. But if you are doing a like a pre-engineering building where you erect one column at a time, then you have to follow this regulation requirements that the minimum number of bolts should be at least 4, and then you will base your design based on that number of bolts, and then you can determine the size, you like the diameter and the embedment. Now, on this one here, so for anchor bolts, this is the typical, or I would say the minimum standard, 3/4 inch, grade 36. So regardless of, you know, um, I haven't actually read it or I haven't seen that in like in writing, but my seniors would always say for a structural application, never use less than 3/4 inch at 3/4 inch. So yeah, so basically, I think maybe he based that um, statement from this, and or yeah, basically minimum diameter of greater minimum 3/4 and then grade 36. Because he specifically told me that never use less than 3/4 inch diameter. So those are the minimum requirements. Now this is kind of like the one that I said, like if you have higher tension due to bending, if say for example if you have a cantilever column or if you are like especially um the the type of structure we have is, I mean, back home is you have a um like a truss, like a truss or something like that one, and then it is resting on a like steel column. It's not fixed here, so that's why you have to have a fixed connection here because this is pin connected at the hands. Unlike pre-engineered building where you have this is also it's either a tapered or standard wide flange. Then you can have moment connection. Then of course you will have a pin connection there. But just in case you have a pin a moment connected, like for example on a crane, like overhead crane, cranes are fixed also at the base because I mean you could do a moment connection like as part like a part of the like pre-engineered building, but if that's a free like a freestanding or standalone overhead crane, then it is just resting on a runway, and then this is um, subjected to bending. Then you have to have a moment. So this is one way of resisting a large bending moment using a. So instead of the usual base plate configuration where you have the column here, and then this is your base plate. Now, for pre-engineered building, the anchor bolt location, this is usually flush, and the anchor bolts are inside. But for moment connected base, the anchor is right outside. Or if you need more, it will be equally spaced from the flange, like that one. This is typical. Even me, I've never seen this kind of connection back then. But there was one or two. In a new design, I used this once, in new design, and then in retrofit, I think I did 3 or 4 projects since coming here. That I utilized this kind of for retrofitting. But for new design, I only use it once, and I will show you that in a sec here. So yeah, so these are the sample details that I did for Angkor Bolts. Now for pre-engineered building, this usually for pre-engineered building, this is already a third-party design. Some like most industrial shops here, like pre-engineered building, are from the US, then ship across the border and installed here because maybe it's way cheaper there to build than here. But there are also Canadian manufacturers here. But most of the time, some of the steel, or I don't know now because of the trade conflict between Canada and US, but it is common to see, like back then, it is common to see a pre-engineered building done in the US than a ship over here. Now, for pre-engineered building, they will design the diameter. They only size the diameter and the base plate. So the scope of the pre-engineered building design is only up to the base plate, thickness of the base plate, and the size of the anchor bolts. Now it's up to the engineer of record, like the building engineer or the say engineer of record for the foundation, to design to make sure that all the forces acting on this base plate can be safely um, carried by the anchor bolts. So they already dictated how many bolts, and most of the time, like use the minimum, which is 4. Although the horizontal load is really small, they always use 4 bolts. And then in large span regional building, sometimes they will use 6. The most I saw was 6, and minimum of force is 4 per O, which is a standard or minimum requirements. Now, there's a provision, or it's not a provision, but more of a recommendation to never use. I already posted this a while ago. Not to use J bolt. uh, So J bolt or L bolt. Not to use this one. There's a recommendation in AIC not to use this one for high tension. So this type of bolt is only used for if your column is only subjected to compression, and very small uplift. I actually calculated the actual like comparing this to the actual capacity of the J bolt versus a threaded rod, because this is the most, or the recommended um, way of um, doing an anchor bolt like a threaded rod. Sometimes you will have some kind of like a ring plate also. If you look at the, especially for uh, I did one like a like I think I have one here. Like I put in the sample, or uh, or this one, yeah, this one here. So if you notice, there's a circle here. That's actually at the bottom right here. And then at the top is more of like a thin plate. This one, you really have to size this one based on the uplift, because this is a monopole and the bending at the base is really high. So I did that one. But going back here, so I calculated the uplift capacity. So the reason why this is not recommended for high uplift, because there's a tendency this will be pulled out from the pulled out from the concrete, because this is, especially this is smooth, so there's a chance that it will be pulled out. The reason why the AIC recommend it really that, because um you have this washer here. You have this washer that will do something like that one, like a cone. It's good for like anchorage. So this is a typical detail with we do for pre-engineered building, subjected to compression, no vertical uplift and shear only, no bending. Now for this one, this is a monopole, plug pole actually, and then um, I size this one for plug pole, but I also use it for like typical detail for light pole, your light standard in parking space. So like again, the same as any um third party or any special structure. This is also done by a third party, and also they will specify the base plate size and then the bolt. Now it's up to the engineer of record again to size the or determine the minimum embedment length, and make sure you meet all the checks. So in this I have a sample calculation later I will show you, but the design I do is this spreadsheet is just for calculating the base plate size if ever I do the base plate design, and then the anchor bolts or design as well. And then this is more of a just determine the size of the plate, or the thickness of the plate, and then the size of the anchor bolt. I don't include in this spreadsheet the design for like the checks for pull out, the checks for pull out. We have the concrete breakout, and then you have concrete dry out, the usual base anchor bolt check. So and then of course the shear. shear strength of the bolt itself. So usually this shear plate, this is already handled by the shear stress of the anchor bolt is already handled by the third party supplier, because they're the one who size the base plate and the size of the or diameter of the anchor bolt, and then they will provide some like loadings like shear, movement at the base, and then I will size the embedment. Now, for since this is closely spaced, like you have reinforcement, this is not like a plain concrete, so you can rely with regards to pull out, you can rely on the transfer of tension to the reinforcement parts. So that's why you have to have a your this one, make sure that with the envelope for the shear plane of the like the cone of the anchor bolt is deep enough, or the embedment of the anchor bolt is deep enough, so that the shear plane will reach the um or will cross into the reinforcing bar. So that's why if there's a force pulling this out, it will engage the rebars. So all I have to do is make sure that I mean before I already did like a minimum embedment based on actual force, but most of the time what governs is, or as long as you make sure that the embedment, the shear plane will cross over like into the reinforcing bars, and that would kind of grab the what we call this one, grab the rebars, and they transfer that to the foundation. If this is pile, then the pile can handle that one, that load. Now there are times also that if I need more, like if the tension is large, and then I need like, like a proper development length of this bar to engage, most of the time I will do like a reinforcement below to ensure that any uplift on the any pull out on the anchor bolt will be resisted by this extra reinforcement, and then it will transfer that this one through like some kind of like a lock. The same as if you have, if you have a tension like in a beam, and then you have a tension bar, or like you need to splice, and then you have to determine the tension on that joint, and then you have to make sure that the lap is sufficient enough to handle that or to transfer that load. So that's same condition. Now the one thing also that I need to well, first this one here, the um this three different um nut. So let's zoom this out. So this is of course, not sometimes, especially if this is outside the building, like exposed to the environment. Some engineers would um, recommend or not recommend, some details don't require grout. All they have to do is you rely on that leveling nut, and that will also serve as, support for the load transfer. Now, some engineers prefer that way. Also, it is easier to design because when it is subjected to bending, there is really no, because like if this base plate bend is not, for example, subject to that for the bending in that direction. So this part here will be in compression. So you will consider the compressive area of the base plate, and then a combination of tension here. Now, if you do a base plate detail the without the grout, then all you have to do is in compression, it's more of the same as in tension, where you have a, if this is and then subjected to that bending, this is intention. This is also the same as the force here because there's nothing supporting the base plate at the bottom. It's just this leveling nut. So whatever, like in the analysis, all you have to do is sum up the forces or the resisting force from all this. These two here are in compression, so it will tend to bend the plate upward, and then or this way concave, and then or is that convex concave, and then this one it will bend the plate this way. So it's easier to size the base plate that way. So that's why some engineers also preferred, and it's easy to balance also. I mean, technically the purpose of this grout is basically to ensure you have a full bearing here. But um, usually for flagpole, the gravity load is really, really small compared to the bending. So that's why some engineers would prefer not to have a um, grout. Now, the purpose of this um, Hicks nut, galvanized CV Hicks nut, this one is the usual, like, you know, the usual purpose of not to tighten this rod. Now the lock nut is more of a it's more of like a how do you call that one? Like a supplementary, like just in case, this one will loosen because this one will be subjected to, cyclic loading. Now over time, this one might get, loosen up. So this lock nut is the one holding it. The if you go to a hardware and then you look for a lock nut, it has a some kind of a, I mean, um I don't think you will get this kind of nut, like especially for big ones in hardware. But if you happen to go to a hardware and then just look at, like, quarter inch bolt sizes, and then you will look for a lock nut. There's some kind of like a silicone or like a plastic inside the thread, so that it will um what do you call this one, uh when you like twist the nut, it would be really difficult compared to a regular nut. If you just, if you screw the nut into the thread, if it's just a regular nut, it would be really easy until you hit the end of the thread. But if you try to insert this nut, once this rubber hits the very top here, it would be really, really difficult doing it by hand. You have to use a wrench. So that is to ensure, like, if there's any vibration, it will not easily loosen up. So that's the purpose of a lock nut. Although some engineers don't require that one, but I typically specify that. And also one thing to consider is, if you notice here, your length of thread. I read it somewhere. The length of thread, you have to ensure that at least a portion of the thread is embedded into the concrete, and that would prevent any. It's more of like a water stop, basically. So it will be difficult for the water to seep into the space here. If you have like a thread embedded into the concrete, so that's the only purpose. It's not a requirements, but it's more of a, it's like, it's been a practice for, old engineers. Like some books recommend that one. So that's why I also recommend that in my details. Now, this is typically a colored, this I think these three here are colored, but since I printed this in black and white, it's not printed as colored one. But or no, not this. I think only this one. This is the extra bar. Now, when I discuss the in our next video, we will be discussing why I'm adding this, adding that what we call this one, extra bar right there. It has something to do with the shear reinforcement, but we will discuss that together with the shear pin. So that's why you will see like a closely spaced ties at the very top. And now see this one, this is all typical grade we specify. So in compliance with the EIEC design guide, although EIEC is not really the proper reference here, but it's almost the same with JEC. Most of the time, the Canadian and American engineers will do collaboration with regards to standards. So yeah, and then the next this one, this detail, this is the one that told you earlier that I only used one time this kind of connection in a new project. And basically what happened on this one was it's cut, but the if you look at the layout of this building, actually it is like this one. So this is the wall, exterior wall, but this one here, the architect put a like extend this grade beam in his design and then serve as a foundation for a sign. This is actually a signage column. There are two of these. So this is extended right here. Then there's another one here. So I only showed one because it's typical and that's normal to do. I mean, if the detail is typical, there's no need to show like the actual like layout. So it's whatever detail here is the same as the other one. So that's why I'm only showing one. Now, the reason why the anchor bolt is on this side, because of course, like I said, it is extended, an extension. And then if you look at if you do a 3D, if we do a 3D, so this is the building, like that one. And then for some reason, he extended this foundation. This is grade beam or piles. And then he put like a wing wall, like a wing wall here, but like a sign. So something like that one. They usually like sign in a like a store or something. So they have this. This is an office, but they have this signage here. So this side here is attached to the main column. This is also a steel structure attached right here, and this is like uh because this is a three-story office, and I think it reaches like almost at second floor at the third floor level. I think this is an old project. I can't remember now, but yeah, that's the idea. So that's the reason why, because this one, once this is like subjected to wind, it will tend to bend this way, right? Although bend that way at the same time this way because it is restrained or not restrained, but it is rigidly attached right here the main building column, and then this one is free, is more, this is more cantilever. So actually this frame, these are all structural members trying to hold this one, acting as a like a cantilever support, and then this bracing is rigidly attached to the column here. So with that, instead of relying on the bracing here to handle all the loads as a cantilever, it's just too big. If I will release if I will release the base here. So what I did was I designed this one aside from this rigidly attached to the main column. I also designed this as a fixed base. So that's why we have this one. And that's the reason why the anchor bolts for tension is on that on that side, because the load is acting in that direction, back and forth. Now, if we do a close-up look on this one, what I did, or what I assume in this design, is I designed the base plate with these bolts here for shear, compression, and tension. Oh no, compression and shear, that one. So, or technically shear, because if it's in compression, all you have to do is just make sure you have the enough base display size. So the mainly for shear, uh, mainly for shear. Now for uplift, I assume, or in my calculation, I assume that only this bolts here is resisting uplift at the same time bending. So whichever direction, for example, if the force is in this direction, so the force in this one would be um, the net uplift on that bolt is minimal compared to this one, because you have the uplift at the same time, uplift due to the overturning. So this is the heavily loaded, and then you just do the same, and then um, you have to make sure also that that load is being transferred to the beam as a torsion. So that's why I have these extra bars that would help with regards to torsion of the beam. So the idea is similar to this one here, like a stool. So once this one is subjected to bending, this one will be in tension, and then the tension is transferred, the force is transferred to this plate, and that plate transferred the force to this plate here, which is welded right here. Then basically that's your load path, and then all the force on the bolt will be transferred down to the foundation. So you have the load from the column. This will be, if this is subjected to bending, so this will be in tension, this is in compression, right? So from this force going to the flange and then into the gusset plate, this one, and then since this is up, it will be transferred to this one, like this will be subjected to like bending downward, and then it will grab the anchor bolt up. So the same as this one. So the load path, this is subjected, for example, in the direction overturning. So the load path would be from column to the wheel here, right? To the wheel, and then transfer that to this HSS, and then into the cover plate, into the nut to the rod, and the rod to the concrete dam. So that's the load path. Now, like I said, I only use this once, like on a new building. The reason why I use that, because I'm restrained with, I mean, this is just a grade beam, and then I relied on the twisting of the grade beam, so I have a solid connection between the column and the grade beam, and that's what I come up with. Um, I would probably the same if it is a wide flange, like unlike this. Yeah, sure, that's fine, but in this situation, if you have two bolts, this is probably the most efficient way of doing it. But in my application here, because this is only what's this size, 10 by 10, so 10 by 10 HSS coulomb, so rectangular, you know, usually call it rectangular tubing or square tubing, but the standard designation for that one is HSS, alloy steel section. And so this is 10 by 10. If I do two bolts, I mean, it will be really close to each other. So what I did is I just, you know, size like single connection, and then just single bolt. And this bolt is Angkor bolt per detail. Where is it? I don't think I have it here, but I think that's, if I remember correctly, that's 1 1/4 bolt. I think, I don't remember now, but I think that's 1 1/4. A36, the same A36 bolt. So that's how you, well, that's how I did that particular application. Like just use like a spool, and the same as this one here. It's just different because I only have one bolt, so it's easier to just use HSS instead of, building a plate like this one. So it's easier to just use HSS. And then, and the reason also why I specify that HSS, because in some location, like other part of the building, I already used this one. So 4 by 4, 1/2 HSS. I think the column at the penthouse. So since maybe during publication they have some kind of extra, so they just throw that there. I only need four anyway. So two on each column and then the other column. Now this is a foundation for a um, mast, like a really um, big, like light, 360 light mast. Um, I can't remember the size, diameter of the pole. I think 16 inch, yeah, 20 inch diameter. And then, like I said, there is um, a circular pattern like the bolt, because it's usually for monopole. The bolt is also already a circular pattern. And then there is a ring, this one ring plate at the bottom and at the top. The top is more of like a template only. And then this is also, well, served also as a template to make sure that all of these are aligned and vertical. And then it will also help with regards to the uplift. And then the same situation here. What I did was I just have to make sure that this one here, the shear, like the shear plane of the cone will intersect with the what do you call this one, aside from the actual, like, pull out from the concrete. And then this is a screw pile, so the all the forces from the pile cup will be transferred to the um usually, if a small pile cup, this is usually like a steel stud, Nilsson stud, not a steel stud, Nilsson stud shear connector. But for this one, this is what, 8 foot 6 wide by 5 foot deep. So I use a 3D rod here so I can have a longer, because I think for Nielsen study are only limited up to 12-inch length, I think, if I remember correctly. Or at least in that particular, I have a catalog of a manufacturer here, and that's what they supply. And then what I did, so instead of Nielsen stud, because I need longer, I just specify a um, 3D rod welded to the pile cap. If this is a concrete pile, then the detail would have been different, because usually for concrete pile, all you have to do is you just extend. This is the pile cap, and then this is the pile, right? Usually this is 3 inches to basically. you have 3 inches cover for the rebar, so you can set your rebar on top of the pile, so it's easy to lay out. Now, this one for concrete pile, what I usually do is just extend the rebar for the concrete pile, extend that one, then add some hook if you need more development length, or if the depth or the depth of this is not enough for the development length, then all you have to do is provide a hook. So extend that one. So that should serve the same purpose as this one. But for this particular project, this is a screw pile. This is a pile cap plate. So there's really no way of, the same as this one where you can extend. So all you have to do is weld a threaded rod on top of the plate and then extend that long enough, high enough so that it will intersect with the shear plane from the anchor bolt. And then this is the plan view. This is the bottom bars. And aside from the usual matting, I have these diagonal bars, that one, so that it will effectively transfer that load from the center going to the piles. It's more of a like a grillage where you have like a cross beam. So imagine, like, just think of this like a cross beam to transfer that one to the pile. So that's the reason why I have that diagonal bar there. So, like I said in my previous video, I discussed about this. I did a quick video regarding base plate, like a reaction video, but it was done in our language. So I will just do this again so that our foreign viewers would be able to understand this one. But basically, what this is this is a base plate design. This calculation is from the EIC Design Guide 1, I think. Yeah, Design Guide 1, because I did this like years ago. So um, that's why it's better to get the latest one, because I don't know what are the changes with regards to the calculation, or maybe there are new, provision that I don't know. But I mean, to me, if this works before, then it works now. That's my view with regards to design. Although there will be um, probably you can minimize, or it will be economical with the latest code probably, but I just don't have time to change my spreadsheet. I mean, this takes time to do this spreadsheets and do all the test run like that. So basically, all you have to do is you will size. So when you have all these forces, compression, uplift, and horizontal, when you size the base plate, you have to size the base plate based on these two loads here. Um, what we call this one, the uplift and the compression. So the compression is based on bearing, bearing of concrete, bearing capacity. So you have to get the ratio, square root of area 1 over square root of area 2. And then, so this is the basically will give you the minimum, dimension of the base plate. Then I will just, use. It's either I will use this exact number or I will upsize it to make it um because all you have to consider also this calculation is just to size the base plate. Now you have to consider all the clearances if this is a wide flange column or an HSS, and then you have to have a bolt. So you have to consider these clearances. Now typically the end distance, this is 1.5 inch or 38 millimeter. So you have to consider that one. So make sure that you have enough clearance, and also this one you have enough clearance from the corner so that you can install this one. You can put the wrench and then torque that one. So you have to consider that. That's why most of the time I will upsize my base plate sizes so that I will meet clearance requirement once I do the detail. Besides this one, if it meets the requirements, bearing requirement based on this dimension, of course, how much more if it's larger? So that's a no-brainer. So it's always as long as your final size here is bigger than final dimension bigger than the minimum required. Now with all this calculation, the same like in the IC design guide recommendation, used A36 steel. So based on compression, I will need this um, thickness. And now for uplift, the analysis is say this one. Let's do that one again. So if this is your column and this is your bolt, so this is your effective length, and then the effective depth. This will project like 45 degrees right here, and that's is this calculation here, and then calculate the minimum based on the same like six from if b is equal to mc over I or m over s. But if it's like a rectangular section, then all you have to do is it's either 6m over bd squared or 6m or 4m over bd squared. If you are using the what you call this one, elastic section modulus. So that's the formula or the calculation. Now again, these are all in AIC design guide. So if you really want to learn about this one, I think it's better to just buy that design guide and then read it yourself, because all everything is explained in there with regards to like any like all assumptions, all considerations. It's in there. Also, um, one of the check that you have to do for plate design is the prying action. So prying action in AIEC design guide, it says that prying action is not really or is neglected in base plate analysis because of um this design. Like as long as you size the you know the base plate based on this analogy, then you don't worry about prying action. But in the in pre-engineered building where you have a you know like a joint at the hands or at the ridge, and then you have two plates here, right, and bolted together, right? That now this one, there are two checks on this one, like thinner plate with large bolt, and then thicker plate with thinner bolt or smaller bolt. So this one you have to consider the prime action, but for base plate, AIC design guide says that you can neglect the prying action in that one. Now, based on uplift, you need 0.88 inch. So therefore, for final sizing, you need the 1.15. So there's no 1.15, so the next size would be 1.25 inch. How much? 1/4 inch, 32. So 32 mm diameter bolt or plate, not diameter. 32 millimeter thick for the base plate because there's no 1.15 thick. So that's 1.25, 1.25 or 32 millimeters. So that's your minimum bolt. And then of course you need to check the weld. Now with regards to the Ancora design, that's why also I mentioned about some engineers also have their base plate sit directly on the concrete, because this would be the reason. So if, for example, this is your column or pilaster or pedestal, whatever you call it, right? And now your base plate is right here. and then you have a grout. That one, that one there, and then this is your column. Assuming there's wide plans, and then for the sake of discussion, we'll just position our bolt right here, you know, or it could be within inside the web. So, for example, that scenario there. Now, if you have a grout, that means you have this, the load, you have the compression or the uplift, and then the shear. Now it will act right here, right? So if you have a space here, like for a grout, what it does is this will increase your bending moment instead of just as pure shear on the, unlike for example, if you have like a pedestal and then your base plate is right here. So your shear plane is right here. So there's, I mean, your moment, the length for the moment would be just the thickness of the plate, because if this is the you know if this is the base plate, this is the hole, and then you have your washer, and then your rod is right here. Then the force is acting at this level, so it will bend with this projection. So the usual P times E, moment is P times E, right? So this is your P, the shear, and then the E, this is your E. Now, if you have a grout, then that will increase the eccentricity or the moment arm. Then that will increase the bending stress on your bolt. So in my practice and other engineers also that I've seen their design, we typically specify maximum 1 inch non-shrink out here. No? Unless the contractor can guarantee, or if if this pile, like the unevenness of this surface doesn't really affect much on the capacity, then you can have no grout here. But if you want a level surface, it's better to allow for a 1 inch grout here, and then just design that with extra moment arm. So that's why in this calculation, so you have the yield strength, then bolt diameter, then bolt hole size, not dimension, thickness, area of bolt, base plate thickness, this one washer. Now in this calculation, um it accounted for the bending, assuming a 1 inch grout. So you have your shear force per bolt, and then bending this one. So bending. So it will include the bending when calculating the um what do you call this one? The In calculating the shear the stress on the total stress of the bolt. So um yeah. So I would really recommend, if you're into designing steel structure, I would really recommend to um buy this design guide. And you will, I mean, it's explained properly. It discusses like the all the assumptions, all the um I would say rule of thumb, or like the like what other engineers are using in practice. So I think it would be a good investment. I mean, it's only like $60. So if you convert that to peso, that would be what, 3,600 if the conversion is 60. That's the conversion today. So more or less like it's less, let's just say less than 4,000. So and then the in return you will have a sound uh, design, you know. It will help your, you know, confidence in that you design your structure properly, because these design guys, these are like, you know, inputs from practitioners also on some research, so you can rely on this design guide, no doubt about that one. So I guess that's it. So like I said, we like in this one here, um, in this calculation and in the discussion, we didn't touch the this check here for the bolt itself. I will discuss that when we discuss our next topic about hairpins on pre-engineered building, because I don't, like me personally, I don't check all of those. I mean, there are only a handful of scenario where I check those using before we have there is like a healthy profis. This used to be free, but now it's you have to you have to subscribe. And then right now I'm using the Simpson Strong Tie Anchor Designer. So if you download this one, this is free. You can use this one. Um, of course, it will use their product. You can also find like, you know, 3D rad design, epoxy adhesive for expansion bolt. Simpson Strong Tie has those types of anchor bolts as well, so no problem. So that's why um, for the last six years, 5 years, I've been using this Simpson Strong Tie, but only if I need to check the concrete breakout, if I cannot have some kind of reinforcement. But most of the time when I do design like this one, I will just make sure that everything is reinforced, like, you know, for pull out, for shear. That's why I have extra bars to transfer that load. Like I said, we will discuss that one, because there's also a question from one of like the members as a group, asking if what's the proper way of anchoring the trusses to the beam and column. So we will discuss that in the next video. So I think that's it for now. So again, our discussion is more of like a, it's not really an actual design, but more of a guide for new engineers. Um, they have the basic knowledge, but don't know like you know, how to start, you know, a proper like step by step procedure in designing a building. So that's what decided me to create this lecture video. So this will be lecture 11 already. You know? So if you are interested, you can watch the previous videos. So this so far these are the topics that we already discussed. The loadings calculation from superimposed dead load to crane loads, funding loads, snow loads, wind loads, and then preparations of framing plans, this diaphragm bracing, shear wall movement frame. So um, this particular discussion, what we're discussing now, this is already lecture. This will be lecture 11, but um, it is more than 11 in total, because I had this divided into, I think, three videos, three or four, can't remember. But yeah, if you just, you know, if you're interested, if you want to see the videos, just go to my page, or you check my page or the group that I created, structural engineering for dummies. And then once you're in the group, just click the feature. If you click featured, pick featured. If you click featured, you will see all the um, um, video that I put in that category. Or you can go check my uh, page, no, video, YouTube video, Bisayang Engineer. Um, if you check, because like in Facebook, you will see like lot of post pictures in between, but in YouTube, I created a playlist and you will see all the videos easily. So yeah, I think that's it for today. And if you have questions, just ask in the comment. Thank you. Ang pagkalaang gayon, minsan na lang wala'y itlog.